Calculating the total number of relations. Welcome, everyone. Today, we are going to dive into a very important topic, calculating the total number of relations. Now, before we jump into the formulas, let's quickly recap what we've learned so far. In our previous lessons, we established a fundamental definition. A relation, which we denote as capital R, from a set A to a set B, is simply any subset of the Cartesian product of A and B. Written as a cross B, this means that every single relation is just a collection of ordered pairs taken from that product. Now, the big question we are tackling today is, how do we actually count them? If we have two sets, how many different relations can we possibly create? To answer this, we aren't just going to guess. We're going to use the precise principles of set theory and combinatorics. Over the next few slides, I will walk you through a step-by-step logical breakdown to derive a universal formula that will make these calculations easy for you. Step-by-step conceptual breakdown. Now that we have established the fundamental definition of a relation as a subset of a Cartesian product, you might be wondering how we actually arrive at a final count. To make this easier to grasp, we aren't just going to jump straight to a formula. Instead, we are going to break the entire calculation process down into 3 logical, easy-to-follow steps. Step 1. Determine the size of the Cartesian product. Now that we have our roadmap for the process, let's dive into the first essential step. Step 1 is to determine the size of the Cartesian product. Before we can find the number of relations, we need to know how many building blocks we are working with. As we touched on in the introduction, the Cartesian product, written as a cross B, is essentially the set of all possible ordered pairs, where the first element, x, comes from set A, and the second element, y, comes from set B. To calculate how many of these pairs actually exist, we look at the cardinality, or the number of elements, in each set. If we say the number of elements in set A is equal to p, and the number of elements in set B is equal to q, then finding the total number of elements in the Cartesian product is quite straightforward. You simply multiply the two cardinalities together. In mathematical terms, the number of elements in a cross B equals p times q, which we write as pq. Keep this value, pq, in your mind, because in the next step, we are going to use it to figure out how many subsets, and therefore how many relations, we can actually form. Step 2. Understand the relationship between relations and subsets. By definition, any subset of a cross B is considered a relation. This is a crucial point to remember. Because a relation is essentially just a collection of some, all, or even none of the ordered pairs we found in our Cartesian product, the total number of possible relations is exactly equal to the total number of possible subsets that can be formed from the set across B. Now that we have determined how to find the size of our Cartesian product in the previous step, let's connect that to the concept of relations. So, if you can find the number of subsets, you have found the number of relations. In the next slide, we will look at the specific formula used to calculate this number of subsets. Step 3. Apply the power set formula. Recall from our study of set theory that if you have a set containing m elements, the total number of possible subsets you can form from that set is 2 raised to the power of m. In our specific problem, we aren't just looking at any random set. We are looking at the Cartesian product, a cross B, which we just calculated in the previous slide to have p times q elements. So, to find our answer, we simply substitute p times q for min our subset formula. By doing this, we arrive at our final definitive formula. The total number of relations is equal to 2 raised to the power of p times q. This formula is the key to solving any problem of this type, as we will see in the upcoming practical example. Now that we've established in the previous step that every relation is essentially just a subset of our Cartesian product, we need a way to count them. This brings us to step 3, where we apply the power set formula. Real-world example. Now that we have mastered the theoretical formula, let's move away from abstract variables and look at a real-world scenario to see how this actually works in practice. Imagine we have a group of students, which we will call Set A, consisting of just two people, Amit and Bina. We also have a set of available school clubs, which we will call Set B, containing three options: music, art, and sports. Our goal here is to find the total number of different ways these students can be related to these clubs. To give you an idea of what this looks like, a relation could mean Amit is enrolled in the music club, or perhaps Bina is participating in both art and sports. It could even be a scenario where no students join any clubs at all. As we move to the next slide, we are going to use these specific groups to calculate exactly how many unique combinations of club memberships are possible. Step-by-step calculation. First, we need to identify the cardinality of our sets, which is just a fancy way of saying we need to count how many elements are in each group. Looking at our set of students, A, we have Amit and Bina, so the number of elements in A, which we call P, is equal to 2. For our set of clubs, B, we have music, art, and sports, so the number of elements in B, which we call Q, is equal to 3. Second, we need to find the number of elements in the Cartesian product. Across B, as we learned in the earlier steps, we find this by multiplying our two cardinalities together. So, P times Q, which is 2 times 3, gives us a total of 6 possible ordered pairs. To make this concrete, let's list them out. We have Amit paired with music, Amit with art, and Amit with sports. Then we and Bina paired with music, Bina with art, and Bina with sports. That makes exactly 6 pairs. Finally, we apply the power set formula we discussed in the previous slide to find the total number of possible relations. We take 2 raised to the power of P times Q. Since our P times Q is 6, we are calculating 2 raised to the power of 6. When you compute 2 to the power of 6, you get 64. So, to wrap this up, there are 64 different possible ways these students can be assigned to these clubs. This includes everything from everyone being in every club to no one being in any club at all. In the next slide, we will summarize the key takeaways from this entire process. Now that we have the scenario in mind from the previous slide, let's walk through the actual calculation step by step to see how we arrive at our final answer. Key takeaways. First, it is vital to keep this fundamental definition in mind. A relation is simply a subset of the Cartesian product. Across B, this is the foundation that allows us to use subset logic to find our answer. Second, remember how we determine the size of that Cartesian product. If the number of elements in set A is P and the number of elements in set B is Q, then the number of elements in across B is simply P times Q. Third, this leads us directly to our master formula. The total number of possible relations from set A to set B is 2 raised to the power of P times Q. This formula accounts for every possible combination, including the empty relation. Finally, I want to highlight a special case you might encounter in exams. If a relation is defined on a single set A, meaning the relation goes from set A back to itself, then our P and Q are actually the same value. In this specific case, the total number of relations becomes 2 raised to the power of n of A squared. All right, we have reached the end of our derivation, so let's pause and consolidate everything we have learned today with these key takeaways. Now, before you move on, please pay close attention to the next slide, where I will highlight some common pitfalls and mistakes that students often make when applying these formulas. Common mistakes. First, a very common mistake is confusing the value of P times Q with 2 to the power of P times Q. I see students often state that the number of relations is simply P times Q. Please remember the distinction we made earlier. P times Q represents the number of individual elements within the Cartesian product itself. But because a relation is a subset, we must use the power set formula, which is 2 to the power of P times Q. Second, watch out for your arithmetic when calculating the exponent. Some beginners mistakenly try to add the cardinalities, calculating the exponent as P plus Q instead of multiplying them. Always keep in mind that the size of a Cartesian product is multiplicative, so you must multiply P and Q before applying them as the exponent. Finally, do not forget to include the empty relation. It is easy to focus only on the active pairings, but remember that the empty set is a valid subset of the Cartesian product. This means the empty relation, the scenario where no element from set A is related to any element from set B, is a legitimate possibility and is included in our total count of 2 to the power of p times q. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls. Even if you understand the formula, it is very easy to make a small error that changes your entire answer. If you can avoid these 3 traps, you will have a much stronger grasp of calculating relations.